So, let us continue our analysis on step index optical fiber. So, we were doing the analysis of this step index optical fiber whose core has a radius a and refractive index n1 and the cladding has refractive index n2. So, what we had done, we had formed equations in capital R in the region R less than a and R greater than a, and these equations have the solutions which are in the form of Bessel functions. So, as we were discussing that in case of planar waveguide for mod x less than d by 2 where nx was equal to n1, I had the solutions cosine kappa x and sine kappa x, while in the region mod x greater than d by 2 where nx is equal to n2, I had solutions e to the power minus gamma x and e to the power gamma x. So, I had oscillatory solutions in the high index region because n1 is greater than n2. So, in the high index region I had oscillatory solutions and exponentially decaying solutions in the low index region, so that the energy is confined in the high index region. Here I have sets of equations. You see this L can take several values, L is equal to 0, 1, 2, 3 and so on. So, for each of these equations I have each of these functions. Okay. For L is equal to 0 I will have j0 y0, L is equal to 1 j1 y1 and so on. So, these are a kind of series of functions, a family of functions j, jl, yl, kl, il. However, in this case in planar waveguide I did not have this kind of situation because the confinement was only in one direction. Here the confinement is also in phi direction. So, from there this L is coming. Okay, if I look at this cosine function, so it is simply if I have a function something like this, then I call it cosine function. Similarly, a function like this I labeled as sine function. Okay. Similarly, if there is a function like this, then I define it as some exponentially decaying, and a function which goes like this I define as exponentially amplifying function. Okay. So, let me treat them just labels. Okay. If there is this kind of variation I label this as cosine x. Okay. If it is, let me put it cosine x itself. Okay. And if the variation is like this, then let me label it as sine x. Similarly, these Bessel functions I will see that what kind of variations they have. Okay. So, let me plot these functions, let me look at these functions and just treat them as some particular variation of x. So, if now for different values of L I plot these j0 y0 and j1 y1 and so on, then I find that j0 has this kind of variation. So, let me just label a function which has this kind of variation as j0, okay, just like the function which has this kind of variation I label as cosine x. Okay. j1x has this kind of variation. So, what I see that these functions have oscillatory behavior. just like the cosine function. Okay. However, as I go in x direction, the amplitude of oscillations, it changes. It is not constant as you have in cosine, and in cosine functions you know that this is pi by 2, this is pi, this is 3 pi by 2, this is 2 pi, and so on. So, but here it is not as simple as that. So, it is some complicated function, but let me say that if this is oscillatory function of this kind, then it is j0, this is j1. If I look at y function, then y function is also oscillatory. Okay, it is also oscillatory, but the only thing is that it blows up at x is equal to 0, y0, y1, y2, and so on. So, these are Bessel J and Bessel y functions, and if I now look at Bessel K and Bessel I functions, then they look like this. So, Bessel K functions, they have asymptotically decaying behavior, okay, and Bessel I functions, they are they are asymptotically amplifying behavior. So, now remember that I want to find out the guided modes. So, which functions to choose in which region, that I will have to take care of. Okay. In the core, I need oscillatory functions. So, of course, the solutions are oscillatory here, but I should pay attention that in the core I have r is equal to 0, and if I have r is equal to 0, then these functions will blow up at r is equal to 0. So, I cannot take these functions. So, I cannot include Bessel y functions in the core. In the cladding, because r can go up to infinity, so at infinity these two functions, these I functions will blow up. So, I will have to discard I functions. So, in the core I will discard this function, in the cladding I will discard this function. So, now I have the solutions, I have the solution in the core, I have the solution in the cladding. So, what are the solutions? So, if this is the fiber, then the radial part has the solution some constant A times JL UR over A in the core, and in the cladding some constant B times KL WR over A. So, these are the solutions. Just like in case of planar waveguide, in high index region I had A cosine kappa x plus B sine kappa x, and here I had C e to the power minus gamma x. Okay. So, similar are the solutions here also. Next thing is now to find out the relationship between B and A and to form a transcendental equation. So, for that I apply boundary conditions. What are the boundary conditions? Boundary conditions are radial part r and dr over dr are continuous at r is equal to A, and since it is weakly guiding fiber, so I can take these as the boundary conditions. So, even though they are not exactly tangential at r is equal to A, but these are approximate, but they are quite valid for weakly guiding fiber. Okay. So, if I put these here, okay, the continuity of capital R at r is equal to A will give me A J L U is equal to B K L W, and the continuity of its derivative at r is equal to A will give me A U over A J L prime U is equal to B W over A K L prime W. So, from here I can relate B to A, and then I can eliminate A and B and get an eigenvalue equations in beta. So, this eigenvalue equation comes out to be, if I divide this by this, U J L prime U divided by J L U is equal to W K L prime W divided by K L W. So, by solving this equation I can find out the modes of the fiber. But this equation has derivative in derivatives in Bessel functions. So, either I numerically solve them using the derivatives, or I can represent them in terms of Bessel functions itself, non-primed functions. For that I can make use of identities of Bessel functions. The Bessel functions satisfy these identities, okay, these 4 identities, and we also make note that j minus 1 u is equal to minus j 1 u and k minus 1 w is equal to k 1 w. So if I use these, then this transcendental equation can now be written in two forms. One is u j l plus 1 u over j l u is equal to w k l plus 1 w over k l w, or u j l minus 1 u over j l u is equal to minus w k l minus 1 w over k l w. So I can get rid of these primed functions here. So as we have been doing the representation of all these equations in normalized parameters, so in fiber also it is worth representing this in normalized parameters and do the analysis in normalized parameters, so as to get rid of any fiber parameters and wavelength. Okay, so we can have independent of fiber parameters and wavelength. So we have already the normalized frequency, which is 2 pi over lambda naught times a times square root of n1 square minus n2 square. You can see that this square root of n1 square minus n2 square is nothing but na, numerical aperture. We define the normalized propagation constant exactly in the same way as we had done for planar waveguide. So it is beta over k naught square minus n2 square over n1 square minus n2 square. And now in order to represent these equations in terms of v and b, I will have to find out u and w in terms of v and b. So what is u? U square is a square times k naught square n1 square minus beta square, and w square is a square times beta square minus k naught square and 2 square, which are similar to kappa square and gamma square of planar waveguide. So from here I can immediately see that this b is nothing but w square over v square. If I take k naught square downstairs and multiply the numerator and denominator by a square, then it becomes w square over v square. So I can immediately get w is equal to v times square root of b, and I already have from previous slide that u square plus w square is equal to v square. Since u square plus w square is equal to v square, then I immediately get that u is equal to v times square root of 1 minus b. So with the help of this I can get the transcendental equation or eigenvalue equation in terms of normalized parameters, and this equation I can put in two categories. One is for L is equal to 0 and one for L greater than or equal to 1. So for L is equal to 0, the equation becomes this: v times square root of 1 minus b j1 v square root of 1 minus b divided by j0 v square root of 1 minus b is equal to v square root of b k1 v square root of b divided by k0 of v square root of b. So you can see on this side I will have k functions, and with k functions I have associated v times square root of b, and with on this side I have j function, and with that is associated v times square root of 1 minus b, because this is u, this is w. For L greater than or equal to 1, the equation becomes like this. So here I have j L minus 1, upstairs and JL downstairs, while I have J1 upstairs and J0 downstairs. Okay, so this is the only difference we should take care of, and also here I have positive sign, here I have negative sign. So for any given value of L, I can have the equation, the eigenvalue equation, and I can solve it for different values of V and generate what are known as BV curves, which are universal curves, So now for any given value of L, if I start solving this equation, then depending upon the value of V, I can have various roots. Okay, and mth root of any equation for a given L will represent LP-LM mode. Okay, LP-LM mode. L represents the solution in phi direction, while M represents the solution in radial direction. What are the cutoffs of the modes? What are the cutoffs of the modes? Well, if you look back, our B is defined as beta square over k naught square minus n2 square over n1 square minus n2 square, and for guided modes beta over k naught lies between n2 and n1, and beta over k naught is equal to n2 defines the cutoff. So, which means that B lies between 0 and 1, and B is equal to 0 corresponds to the cutoff. So, the cutoffs of the modes are defined by B is equal to 0. So, if I put B is equal to 0 here, I will get the cutoffs for different values of L. So, for L is equal to 0, this is the equation, and if I put B is equal to 0, then the cutoffs are defined by Vc J1 Vc is equal to 0, where Vc are the cutoffs. Okay, Vc J1 Vc is equal to 0. For L greater than or equal to 1, the cutoffs will be defined from here, which are JL minus 1 Vc is equal to 0. So, from here I can get the cutoffs of various modes. If you remember, in case of planar symmetric waveguide, the cutoffs were very simple. Okay, cutoffs were Vc is equal to m pi by 2. So, for mth mode you have the cutoff m pi by 2. Okay, so T0 mode no cutoff, T1 mode pi by 2, T2 mode pi, and so on. But here I will have to find out the zeros of these Bessel functions to find the cutoffs. There they were the zeros of tan Vc and cot Vc, but here they are the zeros of J1 Vc and Jl minus 1 Vc. Okay. So, let us first find out the cutoffs of L is equal to 0 modes. Cutoff condition is Vc J1 Vc is equal to 0. So, of course, the first root is Vc is equal to 0 itself, and then let us look at how J1 varies with x. Okay. So, if I plot J1x, then J1x looks like this. Okay. Its first 0 is at x is equal to 0 itself, and that is coming from here also. So, first root is of course Vc is equal to 0. Now, let us look at the second 0. Second 0 appears somewhere here near 3.8, and then the third 0, fourth 0, and so on. So, if I list the zeros of J1x, then they are 0, 3.8317, then here it is 7.0156, and then here it is 10.1735. So, this is the cutoff of LP01 mode. Okay, this is the first mode, L is equal to 0, and first mode is M is equal to 1. So, LP01, this is m is equal to 2, so LP02, m is equal to 3, LP03 and so on. So, I have the cutoffs of various L is equal to 0 modes here. Let us look at the cutoffs of L is equal to 1 mode. Okay. L is equal to 1 mode has cutoff condition J0 Vc is equal to 0, because it is Jl minus 1 Vc is equal to 0 and L is equal to 1. So, it becomes J0 Vc is equal to 0. You should remember that Vc is equal to 0 can be the cutoff of only one mode, and that is the fundamental mode. Okay. So, this cutoff cannot be shared with any other mode. However, non-zero cutoffs can be shared with other modes. So, what are the zeros of J0 now? Let us plot J0x, and J0x goes like this, and we find that the first 0 is around 2.4 and then and so on. Let us list the zeros of J1x, J0x. First 0 is 2.4048, second is 5.5201, third is 8.6537 and 11.7915 and so on. So, you have L is equal to 1, M is equal to 1, LP11, L is equal to 1, M is equal to 2, LP12 and so on. So, you have the cutoff of LP11 mode this, LP12 mode, LP13, LP14. So, all LP1M modes you have here. Now, let us look at L is equal to 2. L is equal to 2, since the cutoffs are JL minus 1 Vc is equal to 0. So, this becomes J1 Vc is equal to 0 for L is equal to 2. So, it is the same as this one. Okay. But I will have to exclude this Vc is equal to 0 here, okay, because this cutoff cannot be shared with any other mode. So, now the cutoffs are 3.8317, 7.0156 and so on for L is equal to 2 mode. So, this will correspond to M is equal to 1. So, LP21 mode, LP22, LP23, LP24 and so on. L is equal to 3 will give you J2 Vc is equal to 0, and these are the zeros of J2. So, you will have these cutoffs for various L is equal to 3 modes. So, in this way, for whatever value of L I want, then I can have the cutoffs. How to arrange these modes? I have so many modes 0 1 0 2 0 3 1 1 1 2 1 3 2 1 2 2 2 3 3 1 3 2 3 3 and so on. Okay. In what order their propagation constants are arranged, increase or decrease. Okay. In case of planar waveguide, it was very simple. T0 has the highest propagation constant, then TE1, then T2, then T3 and so on. Okay. So, the propagation constants they decrease with mode number, but here it is not obvious, and also the cutoffs you can see the numbers are weird. So, I cannot fit any pattern there. In planar waveguide it was very simple, T0 mode 0, T1 mode pi by 2, T2 mode pi, so m pi by 2 as mode number increases. So, the cutoffs are every pi by 2 there is a cutoff of the higher order mode, the next mode. But here I will have to really look into these numbers and then put them together. So, I will have to arrange them in order of their cutoffs. Then we can generate BV curves. So, I choose L is equal to 0 and solve the transcendental equation corresponding to L is equal to 0 and list the highest root always. Okay. List the value of highest root and plot the value of highest root as a function of V, then it will go like this. This is LP01 mode, the highest root. Okay. The first one corresponding to L is equal to 0. So, this is LP01 mode, and this is the fundamental mode. This is the fundamental mode. Its cutoff is 0. So, this is always guided. This is always guided, and remember that we are doing the scalar analysis under weakly guiding approximation. Okay. So, they are LP modes. In terms of vector mode, they are different. Okay. In terms of vector mode, they are different. So, we are not going into the details of vector modes, we will confine ourselves to the scalar modes in this course. Now, what I see that the cutoff, the next cutoff appears for LP11 mode. So, this is 0, the next number is 2.4048, okay, which corresponds to LP11 mode. So, now I plot the propagation constant of LP11 mode, that is the highest root corresponding to L is equal to 1, which is LP11. So, I plot the propagation constant of that with respect to V, and it goes like this. So, this is LP11 mode and it is cut off at 2.4048. Okay. If I look for the next number, I find the next number is 3.8317 and it appears twice here for LP02 and LP21. So, both will start from here at 3.8317, and then if I solve the transcendental equation corresponding to these modes, then the propagation constant vary like this. So, LP21 mode goes like this and LP02 mode goes like this. Similarly, the next one is LP31 and the next one is LP12. So, I can see that a fiber would never guide 3 modes, either there would be 1, 2 or 4, okay, 1, 2 or 4, because these two modes share the cutoff, these two modes share the cutoff. So, these are V versus V curves and the cutoffs of various modes. Now, if I want to find out how many modes are guided, then it is not as easy as it was in case of planar waveguide, that I just calculate the value of V, divided by pi by 2, get the number and find the closest but greater than the integer for corresponding to that number, but it is not that easy here. Here what I will have to do, if I have a fiber and wavelength, I calculate the value of V and then find out what modes are guided and what modes are cut off, okay, looking into these numbers, and then only I shall be able to find out the number of modes, okay. So, in the next lecture I will look into the modal fields and I will work out some examples also on number of modes and what happens if the value of V is very large, then what are the approximate number of modes. Thank you.